Okay, g'day everyone. In this tutorial video I'm just going to go through a very basic linear regression. In fact, we're actually going to do a multiple linear regression, so we're going to be dealing with multiple variables. However, it still will just be a linear regression. Now, in terms of what you've been taught in class, the complexity of the regression modeling that we've looked at goes above what's actually covered in this video. And how I'm going to handle this situation is that I'm more than happy to do up another couple of videos whereby I increase the complexity of the regression analysis that is performed, but I'll base that upon user requests that you can make by either shooting me a message on Facebook or commenting on when I post it up on the official Facebook page. Okay, so let's just dive into a really simple example. So the data that I'm working with is the candle data. So if you go again to the prac materials, you'll see that I think it's got candle in the title. I can't remember actually. I should be able to scroll up and tell you exactly what it is. It just says candle.mtw. So anyway, if you look on the prac stuff, you'll see that one is to do with candles. Anyway, the thing that we're looking at in this case is the most basic form of regression is when we're just dealing with examining the relationship between continuous variables. Now, it can be extended, absolutely can be extended into discrete cases. However, I'm just going to start off with the most basic situation, which is just dealing with continuous. So as we can see in this data set, we've got 3 continuous variables. And what I want to do in this case is I want to analyze how the n length is affected by 2 other continuous variables that are composed or are part of this data set, I should say, sorry. So we've got the initial length and the weight. Now, I'm running Minitab 17 here, and I know for the majority of you, you'll probably be working on the lab computers, which are running version 16. I'm sorry I wasn't able to get a copy of version 16, and I'm not able to record this at uni, obviously. So I'm going to go through the instructions as per Minitab 17, and I believe you should be able to follow those for Minitab 16. However, please let me know if you run into any difficulties. Okay, so the first thing that we need to look at is essentially, obviously, identifying the situation. So again, really what we're doing is here you don't have to type something like this. Here we wish to analyze the relationship between a continuous response variable with 2 continuous predictor variables. So in this case here, the response variable is the n length, and the predictor variables are length and width. As all variables in this case are continuous, we will perform a regression. Well, in this case, we're performing a linear regression. So essentially what we want to do is we want to fit an equation of this form. So you're probably used to seeing straight line equations of this form. So y equals mx plus c. This is just essentially another reformatting. Well, if you want to include further variables into it, so it goes from being a straight line to a plane, and then if you include other variables into hyperplanes, that's perfectly fine. The same way of thinking applies for when you're just dealing with the y equals mx plus c, the 2-dimensional case, as it does for the 3-dimensional and 4-dimensional. It does make things a little bit more complicated, but when you're looking at a model of this simplicity, where we're just looking that each variable is operating as its independent source, so to speak, then it becomes relatively simple. Now, basically, what we want to test is whether or not each of the predictor variables are actually having an influence on the n length. So if we have a look at this model, essentially how this translates in terms of the mathematical model is, if length is providing no information whatsoever, then b1 would equal 0. So in terms of constructing the null and the alternative hypothesis for each of the variables, we need to, it's centered around these constants. So if length is playing no part, then the regression analysis should show that b1 is equal to 0, i.e. 0 times anything produces nothing, so it would be contributing nothing. So when you're constructing the null and alternative hypothesis, make sure it's clear exactly what each of the b1s and b2. So I would state the equation. So yeah, we'll perform a linear regression. So you're performing it on this, and then when you say the null and alternative hypothesis, when you're labeling the b1, b2, we know exactly where it's coming from. But if you want to be 100% complete, so to speak, not so much complete, but if you wanted to go into more detail, you could go for length in this situation, and then the next one would be for weight. And we have a null and alternative hypothesis. And the same reasoning applies for B2 as it does for B1 in terms of 0 and non-zero. Okay, so what we need to do is we need to obviously perform the regression analysis. We're going to get Minitab to do that. So you can just write Minitab output. That's what I like to do. And let's jump into it. So again, remember, I know things will be slightly different if you're doing it, but essentially, if I remember correctly, if you go to regression, the top option is just regression. So if you go to that, that's exactly the same as what I'm going to do now. So we're doing a fit regression model. And I know that I know it looks a little bit different to what you've got here, but essentially the response, you can have multiple responses, but in this case we're only looking to have a single response variable. And in that case, this is the end length, and the continuous predictors, or the values that we want to be able to predict, that is the initial length and the weight. Now you can include categorical components into it. I'm not sure if it allows you to do that by default in regression, but there are ways in which you can include categorical variables into your analysis. That was covered in the previous lectorial. Rob, I know I did the lectorial with Rob, and he covered a situation in which you can include a categorical variable and see how that influences. Because in a lot of cases with this sort of modeling, the other categorical variables, so in our case we've got color, packet, angle, can have a serious influence. And when you do a regression analysis and you exclude those variables, you are essentially excluding what could be very, very useful information in terms of how we understand the key thing, which is the end length in this case. In terms of the graphs, we want to convert this to standardized. I'm not sure if it gives you that option in 16, but if it does, go with that. If it doesn't, it's okay. And then in terms of the plots, we just want to have these two. So we use these two, very similar to two-way ANOVAs and one-way ANOVAs, to test the assumptions of the model. So let's just click OK, and we get this output. So I'm just going to move these two onto the side. We're going to copy everything that Minitab has given us. Don't worry if it doesn't look exactly the same. They may have made some changes in between. The key things that we're looking at have stayed the same. So we're going to send those selected lines to Microsoft Word. And here we've got it. So the p-values, obviously, is the first thing that we need to talk about, as with any sort of hypothesis testing. And in this case, we've got two p-values. So as you know, we've got a p-value for the initial length, and we have a p-value for the weight. And so we need to talk about each of those. We need to talk about how to interpret those p-values, and we also need to be careful about the way that we construct it, because we need to, as I said, to just like when we're doing the two-way ANOVA, because even though these initial p-values are just looking at these variables individually, they are taking into account the effects of the other variables. Now the constant here is actually another term in the model. So you'll see that the line of best fit that it's come up with has this constant in it. That constant is a variable. It's just a constant variable. So it too has its own p-value to see if it's significant. You're not really interested in that for this analysis. What we're interested in is to see if the variables are are important, or should I say, are playing a major role in how the end length is being determined. So in this case, for the first one, we've got initial length is equal to 0.018, so we've got 1.8%. I don't have the sheet, Rob sheet from week, I can't remember exactly what it was, but it was the week that we covered chi-squared test of independence. If you look at his summary sheet for that week, it has a table how to interpret the p-values. And I'm pretty sure when you've got between 1 and 3%, that means we have strong evidence. So we don't have very strong evidence, but we have strong evidence against the null. So strong evidence against the null. So before we go null hypothesis. So before we go any further, we could do the exact same thing for weight. So for weight, we see that we've got a p-value of 0.0. So to 3 decimal places, it's equal to 0. So in this case, we have very strong evidence against the null hypothesis. And I could have copied and pasted that, which I probably should have done. Okay, so by saying that we have very strong evidence against the null hypothesis, that means that we want to accept the alternative hypothesis in both cases. And by accepting the alternative hypothesis for length and for width, that's saying that B1 and B2 are non-zero, and as a consequence of that, length and weight are contributing significantly to how the end length is being derived using this equation. Okay, so as a result, we observe that the initial length, sorry, just trying to think of the best way of wording this. As a result, we observe that the initial length is significant in how the end length is calculated, taking into, or should I say, again, I'm just trying to remember exactly how it's worded in lectures because I'm trying to keep it as close to that as possible, taking into account the effects of the other variables, or in this case the other variables would be taking into account the effects of the weight. So if you have multiple variables, say you had 3 or 4 variables, just write take into account the effects of the other variables. Here we've only got 1, so I'm going to do that. Okay, so this is going to be exactly the same, except I'm just going to be reversing weight and initial length. So we're going to see that this will be weight is significant in how the end length is taking into account the effects of the initial length. Okay, so we've talked about the p-values, which is great. We found that both of the elements within our model are contributing, which is fantastic. We now need to talk about the r-squared adjusted value. So here, where are we? So the r-squared adjusted here, I'm not going to use the r-squared predicted, I believe it is. We're just going to use that. So as r-squared adjusted is actually I'll write it differently. The r-squared adjusted of 52.9% indicates that 52.9% of the variation in the model, in the data, is being explained by the model after normalizing, or after making relative to the number of terms in the model. So I'll explain what that means. It's relatively simple. Basically, when they're talking about the variation here, we're talking about the difference between the model that has been created and the actual observed data. So as with any sort of line of best fit, we're trying to get the model that we've got to be as close to the points, and in this case it's doing, you know, a 50% job. So it's capturing about 50% of those data points, or not so much 50% of the data points, but 50% of the variation between the observed data that you've collected and the data that's generated from the model. Okay, so it becomes as simple as that. Talking about making it relative to the number of terms in the model is just referring to what the r-squared adjusted represents. So it represents a percentage of the variation of the data that's being explained by the model relative to the number of terms. And I talk about this more in the one-way ANOVA and the two-way ANOVA, so please go to those or comment on this video and I'll get back to you as soon as I can. Okay, I'm just thinking about what else needs to be discussed. We definitely need to, I forgot we need to include the r and the x values. So we may actually just, we may do that now. So we'll talk about the r and the x values. Now you don't have to title it like this, I've just done it so it's easier for when you're reading it through. These r values refer to extreme residuals. So by extreme residuals, that just means, in terms of the line of best fit, and I know I did a very simple diagram of this. Look at this, I'm still using XP, the version of Paint is ridiculously old. So, okay. So if we just draw on some points here. Oh, they're terrible. What am I doing wrong here? Yeah, so that'll do. I hope you can see that, sorry. So let's just say we're just doing these points here. Alright. Now, if we do a line of best fit through that, which I'll do by the blue, that's essentially what we're doing here. The residuals is essentially just, well, it is exactly referring to the differences. And occasionally you'll have an incredibly large residual. So we go back to the red here and the dot. So let's just say one of the points, oh, that was wrong, say it was down here. Then that's an incredible, whoops, sorry. That's an incredibly large residual in comparison to the rest of them. So those incredibly large residuals will always be displayed here. And the reason why they're displayed is because these are having a significant impact upon the r-squared term that we've got. So the r-squared becomes much harder to gauge when you've got a lot of these extreme residuals. it becomes a much better indicator when there's less residuals. Now, the general rule of thumb, if I remember correctly, is you're allowed to have, it's either 10% or 8% of your data points being R values. So in this case here, I believe, let's have a quick look, I'm not sure how many there are. There's, where are we? 96, so there's roughly 100, so that means that, say, you've got, say, between 8 or 10 points. In this case, we've only got 6, so we're okay no matter what. So we observe there are, in this case, 6 large residuals. However, given this is less than the maximum, and please double check actually with Rob or or anyone, I should say, sorry, within the team about that point. I'll probably find out as soon as I stop recording this. Given this is less than the maximum allowed, I'm just going to guess here it is 10%. We remain, or you can just say the results of the analysis are, however, given this is less than the maximum allowed, I'm just going to make it really simple. We are not concerned. Could be worded a bit better than that. These X values don't refer to residuals, but they refer to values that have had a significant impact upon these upon the calculation of each of these parameters. So they just, as I said, it just represents an unusual value, and usually they could be possibly outliers. So the general rule of thumb is when you have a look at these X values is have a look, it'll tell you exactly where it is, so observation 30. So if we go to observation 30, scrolling, where are we? Here, it's saying that it appears to have an incredibly large value. So remember the end length that we've got within here. So we've got this, maybe this initial length or this weight is considered to be large. But either way, when we take these data points and we compare them against the model, there seems to be a large difference. So you just need to make mention of that. Given that you've only got one, we don't really need to talk about it. Now, in terms of the assumptions of the model, we need to have normality of the residuals. This is exactly the same as what we have for the one-way ANOVA and the two-way ANOVA. So what I'm going to do is just move that down, and this is the plot that we're looking to get. So we're going to right-click, send the graph to Microsoft Word, and we see here that we've got within the normality of the residuals. So the way that we assess that is the straight line is the idea of having a perfectly normally distributed set of residuals, and these dot points refer to what actually exists within the data. So the closer these points are to the line, the better. So again, here we observe that outside of a few points on the tails, the residuals are normally distributed. Hence, the assumption of normality of residuals is satisfied in this case. If it wasn't satisfied, just as like I said in the previous videos, it doesn't mean the results of the test are wrong. It just means that they may not be reliable. Okay, the second is to test equal variances. Exactly the same as what we have with one-way ANOVA, two-way ANOVA. And we do this by inspecting, where do we go? So we want to send this graph to Microsoft Word by expecting the residuals versus the fitted value. You may not have standardized. If you've just got residuals versus fitted values, that's fine. So let's just move that over. Okay, and so now we just need to talk about our assessment of this in terms of whether or not it's random or not. Now, if it's a bit harder to isolate or to determine whether or not there is a pattern of equal variances or non-equal variances. But essentially what we want to see if we have equal variances is that for the different groupings of data, they should be producing similar results. And so what I mean by that is if there appears to be any sort of relationship in the residuals, like for instance, you know, you had some sort of curvature within it. So if I just delete this, whoops. So for instance, I'm not sure if I've done the right one, but Control Z. Where am I? Completely hopeless with this stuff. So if you had something that looked like that within the data, for instance, like if the data was sort of centering around a curve like that, then that would be an indicator that the variances aren't equal. It's following some sort of a pattern. They also have what's known as a fanning effect, and that's when you start to see something like this within your data. So you might have something where the data starts to look like this, or alternatively, it may look like that. Or it could be a combination of the two. Then those sort of effects where it just appears as though there's something else going on indicates that we probably don't have equal variances. Now this is something that we're not going to heavily penalize you on, so don't freak out about it. But essentially, if there's no relationship whatsoever, equal variances is usually indicated by common patterns that we see within the data, by not observing significant differences within it. So we do seem to have a lot of random scattering there, and there does seem to be a bit more of a cluttering here, which possibly indicates that maybe the variances in this case are not equal. So it's in this case it's not very strong. I'm just saying as a loose indication. If this was really dense and this was really random, then I would say definitely we don't have equal variances. But because this isn't heavily densified, if you will, and this is still pretty loose, I would say that the assumption of equal variances has probably been satisfied in this case. So the residuals versus fitted values do not appear to show any strong trends of non-equal variances. As such, the assumption of equal variances is satisfied. Okay, so now we've had a look at the assumptions of the model, being the normality of the residuals, which we've got here, and that we have equal variances. As they've both been satisfied, we can be confident that the results that we've got are probably really good. So we just need to have a very short conclusion on that, as both of the assumptions of the model appear to be satisfied, we can be confident with the results of of the test. And you can write regression if you will. So anyway, I'm going to leave it there. As I said, I'm more than happy to go into much more complicated versions of regression analysis, but I just want to get to gain to understand exactly where you guys may be lacking in the regression analysis before I do it, because there's so many different things that can be covered. So anyway, I hope you enjoyed that, and as I said, comment on the video, send me an email, send me a Facebook message if you've got any questions or any comments about the video, and I'll get back to you as soon as I can. Okay, thanks. Bye.